Hey everyone! In this video, we're going to do almost the same exact problem that we just did. Except the difference this time is you can see we're only taking a sample of 15 batteries instead of a sample of 50 batteries. Since 15 is smaller than 30, I know that I'm using a hypothesis test for the mean small samples. Now, how do I know it's still a hypothesis test for the mean? Because I'm given a mean and standard deviation of a sample. So, notice, follow steps 1 through 3 from hypothesis testing for large means, because all of that stuff is the same. The thing that's different is how we calculate the p-value. So I could copy and paste a lot of this stuff over, but I'm going to start from scratch and go through this process again, but I'm going to go a little bit quicker. So we know that our null hypothesis is going to be that mu is 1.5 hours. An alternative hypothesis, which is the claim here, is that mu is actually bigger than 1.5. Now we need to identify what x bar is, what mu is, and we need to know what the standard error is. X bar is still going to be 1.55. Mu is still 1.5. The standard error is going to be a little bit different because our sample size has changed. So we're going to take the standard deviation and we're going to divide it by the square root of n, which in this case is only 15. So you can see that's a larger standard error. Now here's the big difference between large samples and small samples. I also need to identify what the degrees of freedom are, which is always one less than the sample size. So that's going to be 15 minus 1. So we have 14 degrees of freedom. And I'm going to need this when I use my t.dist function. So I'm going to use t.dist instead of norm.dist because we are no longer dealing with an exactly normal distribution. Remember, we're padding a little bit on the extremities to account for the fact that this is a small sample. But before I can do any of that, I need to find the t-value for this particular data that I'm given. So t is calculated. You can see it's written right here. My t-value is going to be x bar minus the mu over the standard error. So that's going to be x bar minus mu divided by the standard error. So that gives me a t-value of 0.60515. So now if I want to find the probability that x bar is greater than 1.55, what's the probability that I would get a sample that happens to be this far away from the mean? I'm going to use my t.dist function, and I'm going to do 1 minus because it's greater than. If you look here, x bar is greater than mu, so we're going to do 1 minus t.dist. And the things we need are just our t-value, our degrees of freedom, and then we're going to say true. So I need my t-value, my degrees of freedom, and then we want this to be cumulative. So we're going to go ahead and calculate that, and we get a probability, a p-value of 0.28. Now 0.28 is larger than 0.10, and so we will fail to reject the null hypothesis. So now we want to verify the fact that we want to fail to reject the null hypothesis. I guess first we want to write this as a sentence. There is not enough evidence at the 0.10 level to support the manufacturer's claim of battery life above 1.5 hours. So now we want to confirm that by constructing a confidence interval. Again, this is a one-tailed test, and so all 10% of our confidence interval is going to be, or all the 10% that's left over is going to be on the bottom half of the lower end. And what I need in order to find a confidence interval for small samples for a one-tailed test is I need to go through a couple of extra steps. So I have to find this critical t-value. And to find that critical t-value, I'm going to use the t-inverse function. And then I'm going to multiply that critical t-value by the standard error. And that will give me something called the margin of error. And then I can subtract the margin of error from the mean, the sample mean x bar, to find my lower bound. I'm not going to find an upper bound here. Notice the or. These steps up here are things that we've already done, and we did in the last example as well. But basically, I have to identify my proportion, which for a one-tail test, talking about the lower tail, that's just going to be my alpha value. So that's going to be 0.10. I need to know the degrees of freedom, which I already know. And that's df, and that's 14. And that's all I need to know to find my critical t-value. So t critical is going to be t dot inverse. And then the only two things we need are the probability and the degrees of freedom. And that gives me my t-value. And then I'm going to take that t-value. Because this is a lower test, it says right here, if you found t for the lower tail, it should have come out negative. Take the absolute value of this number. So what I really want, undo. So what I really want to do is take the absolute value of this number because I want t critical to be positive. Notice it's the same value, it's just positive now. And I can find my margin of error, which is E, by taking my critical t-value and multiplying it by the standard error, and that gives me 0.111. So now, my lower bound is going to be found by taking the center of my confidence interval, which is x bar, not mu, and subtracting 0.111 from it. Now that gives me 1.438. Since that's just a lower bound, anything above 1.439 is in my interval, in my confidence interval. And we're checking, is mu in that interval? Well, yeah, it is. 1.5 is greater than 1.439. So this confirms we should fail to reject the null hypothesis since mu is contained in our confidence interval. So far, we've decided between using our hypothesis test for the mean for a large sample, and then we decided for a small sample, we worked out essentially the same exact problem for two different scenarios, one large sample, one small sample, so that you could see the difference between the two. In the next video, we're going to go through these processes again, but we're going to be given the original data, and we're going to be dealing with a different type of tail in our hypothesis.